Welcome to this explainer. Today, we're diving straight into Chapter 2.5 of our source material to explore the absolutely fascinating world of textiles. We are looking at the alchemy of color, the science, engineering, and art of textile dyeing. If you've ever looked down at your favorite shirt and wondered how it got that incredibly vibrant hue and how it actually kept it after dozens of trips through the laundry, well, you're in the exact right place. We are going to go on a journey today, starting way down at microscopic chemical bonds all the way up to the massive global ecological impacts of our clothing. Let's get into it.
Here's our roadmap for the explainer. We'll cover 1. The physics of dyeing. 2. The dyeing process. 3. Harnessing natural colors. 4. The synthetic revolution. 5. The ecological toll. And finally, 6. Balancing art and science.
So to start, what actually is dyeing? Well, it's way more than just painting a surface. By definition, dyeing is the coloration of textile materials through immersion in an aqueous or water-based solution. The absolutely crucial takeaway here is that it relies on organic dye molecules permanently altering the optical properties of the substrate. It's not just some temporary coating that flakes off over time, it's a fundamental, permanent transformation of the material itself.
Let's kick things off with Section 1, the physics of dyeing.
To achieve that permanent coloration we just talked about, organic dye molecules have to actually physically penetrate the internal fiber structure. Think of the fiber polymer chain like a really complex lock, and the dye molecules hovering above it as specific keys. They don't just sit on the surface, they have to structurally bond and chemically react. This happens through specific functional groups forming ionic bonds, covalent bonds, or van der Waals forces. That invisible, microscopic chemical reaction is exactly what allows your clothes to withstand repeated washing.
Moving right along to Section 2, the dyeing process.
In the real world, getting those molecules to bond comes down to a highly controlled 3-step aqueous diffusion process. Step 1 is immersion, literally just getting the raw material into the dye bath. Step 2 is diffusion. This is where the dye molecules start actively moving through the water toward the fibers. And step 3 is penetration and fixation, where those lock-and-key chemical bonds we just learned about finally snap into place. And what's cool is this can be executed at almost any production stage, whether you're dyeing raw fiber, spun yarn, massive rolls of fabric, or even a completely finished garment.
But here's the catch. Those dye molecules, they won't just neatly diffuse and fix themselves perfectly on their own. Forcing this molecular diffusion requires energy and chemical catalysts. First, we need heat to provide the active energy, getting the molecules in the water agitated and moving. We also absolutely need electrolytes, like salt or soda ash. These actively push the dye out of the water and into the fiber structure. And finally, auxiliaries, like leveling agents, are added to the mix to make sure the color goes on smoothly and evenly. It's a very dynamic, complex recipe.
Which brings us to Section 3, harnessing natural colors.
Historically and chemically, there is a massive fork in the road when we talk about where our colors come from. We have two very distinct origins. On the one side, we have natural dyes, which are extracted from renewable vegetative matter, things like seeds, leaves, roots, and bark, as well as animal residues. On the other side, we have synthetic dyes, which are chemically synthesized organic compounds engineered in labs. We're going to start our journey by exploring the natural side of this tree.
There is an undeniable ecological brilliance to natural dyes. They are extracted entirely from renewable natural systems. And what I find really fascinating is that dye-producing plants often thrive on marginal wastelands. That means they don't have to compete with or deplete the essential agricultural land we need for food. Plus, natural dyeing can actually operate on a zero-waste cycle. The residual process waste from materials like harada or indigo acts as an incredibly rich agricultural fertilizer once the dyeing process is totally finished.
But here is a wild chemical trick. A single natural dye source, like the madder root, can actually shift into an entirely new, broad color spectrum based on the specific metallic compound, which is called a mordant, that you apply to it. Adding copper sulfate gives you these vibrant greens. Ferrous sulfate pushes that exact same root toward dark blacks. And alum yields rich, classic reds. Essentially, these metals act as the essential chemical fixatives and modifiers.
However, the aesthetic beauty of nature comes with some pretty severe limitations. Natural dyes suffer from unpredictable seasonal variations. Your color yield changes entirely based on the crop season, the location, or even just plant maturity. They're also highly pH sensitive, and they often have poor fastness, meaning they fade pretty easily in the sun or when exposed to sweat. But perhaps the most surprising limitation is the effluent problem. While the plant dyes themselves are biodegradable, that heavy reliance on metallic mordants we just talked about, that creates substantial, hazardous residual wastewater. It's actually a huge misconception that natural automatically means it's totally harmless to the water table.
Now let's pivot sharply to Section 4, the synthetic revolution.
Shifting to the other side of our chemical tree, we have synthesized molecules. These were engineered specifically to mathematically solve nature's limitations, prioritizing precision and massive commercial scale. For instance, microdosing means you only need a tiny drop of colorant to dye vast commercial quantities of textiles. You also get an infinite gamut, which gives you an unrestricted spectrum of colors. And that leads to flawless reproducibility across massive global production runs. It ensures that a shirt manufactured today is going to perfectly match a shirt made a year from now. And finally, you get maximum fastness, offering superior chemical resistance to fading and washing.
All of this builds into an incredibly strict system of chemical engineering known as the synthetic affinity matrix. Remember our lock and key analogy from earlier? Well, synthetic dye classes possess extremely strict molecular fiber affinities. Cellulosic fibers, like cotton, require direct, sulfur, vat, or reactive dyes. Protein fibers, like silk and wool, require acid or metal complex dyes. And synthetic blends, like your polyester workout gear, rely completely on dispersed dyes. You can't just use any dye on any fiber. The chemical structures have to align perfectly.
That brings us to Section 5, the ecological toll.
Now, we have to look at the macro level, because the commercial perfection of synthetic color carries a very heavy environmental weight. First, there's the chemical dependency. These synthetic processes demand massive volumes of those electrolytes and chemical auxiliaries we discussed to force diffusion at scale. Second is effluent pollution. Because synthetic dyes are built on non-renewable petrochemical bases, the residual chemicals result in severe soil and wastewater toxicity if they're released. Which leads directly to the third point: operating responsibly demands vastly expensive, incredibly strict effluent control and mitigation infrastructure. Literally, it is a highly toxic process if left unmanaged.
Let's bring it all together in Section 6, balancing art and science.
When we actually weigh these two systems side by side, the trade-offs become incredibly clear. Look at the source material. Natural dyes rely on agro-renewable sources, while synthetics rely on petrochemicals. For reproducibility, nature is highly variable, but synthetics offer a flawless mathematical match. When it comes to color yield, natural dyes require massive raw input for a very low yield, whereas synthetics require just micro quantities for a huge yield. For chemical fixation, natural dyes lean heavily on metallic mordants, while synthetics demand salts and auxiliaries. And finally, ecological impact. Natural dyes are inherently biodegradable, but present very real localized mordant toxicity issues. Synthetics, on the other hand, present broad, high wastewater toxicity that requires incredibly strict treatment control.
Which leaves us with this final, really provocative thought. Mastering the dye bath truly is the past, present, and future of textiles. It's this delicate, crazy equilibrium of physics, chemistry, and art. So, the question we have to ask ourselves as we look at the clothing we put on our bodies every single day is this: will the future of textiles harness the erratic, biodegradable beauty of ancient natural extraction, or are we going to continue to lean entirely into the infinitely reproducible, engineered precision of modern synthetics? It's a complex global balance for sure, with absolutely no easy answers. But I hope this explainer has given you the clear framework to understand it. Keep learning, and I'll catch you in the next explainer.